Hello, Chemistry 12. This is Mr. Chan. And today I wanted to talk about a topic called hydrolysis. Now, what is hydrolysis? Is that hydrolysis is an interaction of ions with water to produce an acidic or basic solution. So the key word here is you want to talk about ions with water. Okay? So an ion would be something like F minus 1 plus water, and you would get some sort of acidic or basic solution. So this is another way of producing an acid or base solution without using a substance like our typical hydrochloric acid or sodium hydroxide base. So basically, how does it work? When a salt, now the word salt, recall back from grade 11 or earlier on, is a metal, non-metal, is dissolved in water, one, both, or neither of the ions will react with water to produce an acidic or basic equilibrium. Now, recall another name for a salt is an ionic compound. Now, there are many different ways to form an ionic compound, but what we're going to do is, since we're talking about acids and bases, we're going to focus specifically on acid-base reactions. So, a salt that is a result of a strong acid and weak base reaction, that will give you an acidic solution. Okay, so strong acid, weak base reaction will give you an acidic solution. Now, we have an example here. So we have HCl and NH4OH. So HCl in this case, this one is your acid. NH4OH, this is your base. And what you have is you have a standard double replacement reaction where you produce water and ammonium chloride. Now, this reaction here, this is a double replacement reaction from Chem 11. Okay, now back in Chem 11 and up to this point, that's all we cared about, your acid, your base, and you get your products. Now what we want to do is we want to focus on the ionic solid that's produced. And in this case, what you want to do is you want to think about what would the ion do? Okay. What would the ions do? And I use the acronym WWID. So when we focus on the salt that is produced, the ionic solid that is produced from an acid-base neutralization, we take a look and say, what would the ions do? And that is where we're focusing on in Chem 12. Okay. Now, so what do you do first? So you recall from grade 11 and even the beginning of solubility, an ionic solid, so NH4, Cl is an ionic solid. And what it will do is, therefore, it will dissociate in water. Remember, dissociation is breaking apart into ions. So therefore, dissociate. Okay. Now, so what we do is we go, okay, NH4Cl will break apart to NH4 plus and Cl minus 1. Now, once we break it apart into their component ions, what we want to do is we want to take a look at where are the ions located on the acid-base chart. So when you take a look at your acid-base chart here, what you want to do is you take your acid-base chart, you look for the ions. In this case, notice near the bottom, you have NH4 plus. Okay. And on the upper right, you have chlorine minus 1. Now, notice the location. Chlorine minus 1 is a result of complete dissociation, while NH4 plus 1 is in the equilibrium section of your acid-base chart. So in this particular case, if we were to take a look at the hydrolysis, what you have is you have NH4. You could have on the left side at equilibrium. Chlorine minus 1 is on the right side not at equilibrium. Now, the key thing you might want to focus on is the fact that one is at equilibrium and the other one is not at equilibrium. So in this case, if NH4 is on the left side at equilibrium, what happens is, therefore, it will react with water. Okay. And what do we mean by reacting with water? Therefore, hydrolysis. Let me just separate this so it's a little bit cleaner. Now, chlorine is on the right side, is not at equilibrium, therefore will not react. Therefore, no hydrolysis. Oopsie. No. Hydrolysis. Okay. Now, so what happens is the two ions will break apart and one will react with water, in this case NH4, the other one will not. And this reaction with water is called hydrolysis. So what will happen is the ion, so what we have is we have NH4 plus and water. Now, since it is found on the left-hand side of the acid-base chart, if we take a look at the acid-base chart, recall everything on the left-hand side of the table is an acid. It will do the donation. So therefore, what we will have is we'll have, in this particular case, NH4 plus will donate a proton to water. And what you get is you get H3O plus and NH3. Since H3O plus is produced, therefore, solution is acidic. Okay. Now, I just want to emphasize a couple of things. You might say, well, Mr. Chan, I don't get it. How can it be acidic? Well, what happens is originally the hydrochloric acid and the ammonium hydroxide react in a double replacement reaction. You get your neutralization, you're done. So what we have to do now is we have to take a look at the ions that are produced from the solid. And because the ions from the solid react with water, the solution is acidic. Okay, so what you would get is you would get a neutralization because the moles of acid is equal to the moles of base. But because of the salt that is produced, the solution would be slightly acidic. All right. Now, I use the analogy something like this. This first equation would be like your mother, your father, married, had you. Okay? You are like the NH4Cl. What you do with your life after you graduate from high school or university is up to you. There's no influence from your parents. Same idea here. So in an acid-base reaction, the hydrochloric acid, in this case, neutralizes the ammonium hydroxide base. We're done. Now we have to take a look at the ions that are produced from the solution and what would they do. Okay, and so that's why you would get an acidic solution overall. Now, conversely, a salt from a weak acid and a strong base will give you a basic solution. All right, now again, you have your acid, which is HCN. And you have your sodium hydroxide, which is a base. Now, you have your double replacement reaction, and what you produce is sodium cyanide. And again, what you want to do is you want to take a look at what would the ions do. Okay, you want to take a look at what would the ions do. So again, you recognize, so sodium cyanide is an ionic solid. So what would happen is it would break apart to sodium +1 and cyanide ion -1. Now, again, what you want to do is you want to look for the location. So in this case, if we look at CN -1, if we look at the acid-base chart, notice, let me see here, where's my acid-base chart? Notice CN -1 is right here. It's on the right-hand side, and notice it is equilibrium. So in this case, if we take a look, we have, it's on the right side. At equilibrium. So since it is at equilibrium, it will react with water or it will hydrolyze. All right, and I'm just going to highlight the word equilibrium. Now, you might say, well, Mr. Chan, what about sodium? We don't see sodium anywhere here on the acid-base chart. So where can we find the information? What would sodium do? In this particular case, if you take a look on page 144 in your reading package, you will see this term says hydrolysis. And if you look on the bottom of page 144, it says, conclusion, spectator cations will be the ions of the alkali metals and the ions of the alkaline earths. Okay, so what is the alkali metals? It's column 1, so the very left column on the periodic table. So things like lithium, sodium, potassium, rubidium, cesium, francium. And ions of the alkaline earths, column 2, beryllium, magnesium, calcium, strontium, and so on. They are spectator ions. They are spectator ions, and what are spectator ions is they do not react. So in this particular case, if we look at this example here, sodium, what you have is a spectator ion. Okay, And this is from page 144. Therefore, no reaction. Okay, now, so in this particular case, you have Cn minus 1. So therefore, we have Cn minus 1 plus water will be in equilibrium with, in this case, it accepts a proton. So you have HCN and OH minus 1. And again, since OH minus 1 is produced, therefore basic. Okay. So again, what you want to do is you notice that you first of all have to take a look at the ions. What do the ions do? All right, are they found on the left side or the right side? Are they at equilibrium? And that determines if they will react with water. Okay, and the other thing that you should be aware of, again, the acid completely neutralizes the base. Why is the solution acidic or basic afterwards has everything to do with the ions and what the ions will do. All right, now let me give you a couple of examples of questions that you might see. So let's say if we take a look at our worksheet, and let's say we look at worksheet number 1B. Now, it says, right, if we take a look, it says here, let me just scroll it down, 1B, do I have it here? Yes. Oh, sorry. That's okay. It says, write the hydrolysis reactions occur when the following solution substances are added to water. State whether the salts are acidic, basic, or neutral in solution. Now, in this case, you are given K2CO3. So K2CO3, they're asking you if it's acidic, basic, or neutral. Again, the first thing you want to do is, since it's an ionic solution, ionic solid, it dissociates into its component ions. So 2K plus and CO3 minus 2. And the second step is, all right, let's take a look at the location. Now, CO3, if you take a look at your acid-base chart, let's see here, where's my acid-base chart? CO3 is, where is it? Where is it? Ah, it's right here. It is at equilibrium. Okay, so if we look back here, you have right side at equilibrium. Again, since you see the word equilibrium, come on, you recognize that it undergoes hydrolysis. So here, therefore, hydrolysis. Now, conversely, if you look on this side, potassium is found in the first column. So therefore, it is a spectator ion. And again, you refer to page 144. So in this particular case, since CO3 will undergo hydrolysis, so we have CO3 minus 2 and H2O. What you get is you get HCO3 minus 1 and OH minus 1. And since OH minus 1 is produced, this would be basic. Now, pretty straightforward. Now, when you take a look at the worksheet, let me see if I can scroll down here without messing up. You notice for 1B, we get a basic solution. Now, you will notice that, let's say the answers to 1C. Notice if there's no hydrolysis, it is neutral. Okay? Should make sense. If the ions do not react with water, the solution should stay neutral. Okay? Now, let's do another one. Let's try question number 2B. Okay? It says, calculate the pH of a 0.03 molar solution of each of the following. Actually, that should be wrong. Okay? So I'm just going to say, come on. pH of each of the following. So let's say we have 0.030 molarity sodium fluoride. So if we flap up to the front here, so we have worksheet 2B. So we have 0.30 molarity sodium fluoride. You want to find pH. So what you want to do is, again, you're given a salt. You take a look in this particular case. Sodium fluoride is an ionic solid. So sodium fluoride will break apart to sodium +1 and fluorine -1. Now, notice we added some numbers, 0.030 molarity. So here will be 0.30 molarity. Sodium will be 0.30 molarity. Fluorine will be 0.30 molarity. Why? Again, is because it's a 1-to-1-to-1 ratio. Now, next step, again, you want to check to see if the ion will undergo hydrolysis. In this case, the sodium will not because it's a spectator. Fluorine, if you take a look, will be yes for hydrolysis. Again, you want to take a look at the location. So here, your acid-base chart. Fluorine -1, where is it? It's right here. Okay. Now, so in this case, we would go fluorine -1 plus water would be in equilibrium with HF and OH -1. And since I'm calculating pH, again, what you need to do is you're going to need to set up your ice tables. Okay, so so if you have your ice, you have 0.30. Here is 0, 0, minus x, plus x, plus x. And what you have is 0.3 minus x, x, x. Now, since you are producing a base because of the hydrolysis, remember it's Kb. So Kb is equal to concentration of HF, concentration of OH -1, all over concentration of F -1. Now, how do you figure out Kb? Remember, Kb is equal to Kw all over Ka. So in this case, it would be Kw all over the Ka of HF would be equal to x squared all over 0.30 minus x. Okay, and you know that here we go. We have 1.00 times 10 to the negative 14 all over Ka of HF, which is 3.5 times 10 to the negative 4 is equal to x squared all over 0.30. Now, again, I could ignore the minus x because the change is very small. Solving for x, so we have 1 e negative 14 times 0.3 divided by 3.5 e negative 4. And then we square root the answer. I get an answer of x is 2.93 times 10 to the negative 6. Okay, I'm just going to double check. E negative 14 times 0.3 divided by 3.5 e negative 4, and then square root the answer. That's right. Now, this is equal to the concentration of OH minus 1. So then what do you do afterwards? Well, you could take the POH is equal to negative log of 2.93 times 10 to the negative 6. Okay. Okay, let's see. Negative log, oopsie, clear. Negative log 2.93 e negative 6. So I get an answer of 5.55 or 5.3, sorry. And then pH would be 8.47. Okay, and that just confirms that you have a base solution. Now, some of you might say, wow, Mr. Chan, this calculation, pretty brutal. This calculation in green is basically the exact same things as you had done with your KB calculations. Okay? You had done that before in your previous calculations. All right? The only thing that is new is that when I gave you the KB calculations, all I did was I gave you the concentration and I gave you the ions in solution. But in this particular case, you had to figure out the ions and what the ions would do. All right, folks, thank you very much. Have a good day. Bye-bye.